In this problem, we are tasked with determining the total number of provinces in a set of connected cities. There are n cities numbered from 0 to n-1. Some cities are directly connected to each other, while others are not. If city A is directly connected to city B and city B is directly connected to city C, then city A is indirectly connected to city C. A province is a group of cities that are directly or indirectly connected to each other and have no connections to cities outside the group. We are given an n times n array named disconnected, where isConnected of I and j equals 1 indicates that city I is directly connected to city j, and isConnected of ij equals 0 indicates that city I is not directly connected to city j. Our goal is to return the total number of provinces. To solve this problem, we use the union find data structure, also known as disjoint set union or DSU. This data structure is ideal for managing a set of elements partitioned into disjoint subsets and efficiently supports two primary operations: finding the root of a set and uniting two sets. It is particularly useful for finding connected components in a graph, detecting cycles, and in this case, determining the number of provinces in a connectivity matrix. Initially, we store the size of the isConnected matrix in the variable n, which represents the total number of cities. We declare an array P to keep track of the parent of each element, or city, and we initialize this array using the iota function from the numeric library. This function fills the array with consecutive values starting from 0, ensuring that each element is initially its own parent, indicating that each city forms a separate set. We then iterate over all pairs of cities ij using nested loops. The outer loop runs from 0 to n-1, and the inner loop runs from i+1 to n-1. This ensures that we only check each pair of cities once, avoiding redundancy. If the cities I and j are directly connected, we find their respective roots using the find function. If the roots are different, it means the cities belong to different sets, so we unite them by updating the parent of one set to be the root of the other. We then decrement the response counter, which keeps track of the number of distinct sets or provinces. Union find, as its name suggests, supports two main operations: union and find. The union operation joins two disjoint sets into a single set, and it uses union by rank or union by size to keep the depth of the tree small by assigning the root of the smaller set to the root of the larger set. The find operation determines the representative or root of an element set and uses the path compression technique to optimize future searches by making all elements in the path from the given element to the root point directly to the root. The find function uses recursion and path compression to optimize future searches. The find function thus declares a lambda function that takes an argument of type int and returns an int. The ampersand in capture by reference indicates that the lambda captures all variables in its scope by reference. In this case, the function find has access to the variable p and can modify it. Scope refers to the region of code where a variable is defined and can be accessed. In the case of the find function, this allows access and modification of the vector p, which is essential for the path find and compression operations in the union find algorithm. The basic syntax of the function is iota of begin, end, and start value, where begin represents the beginning iterator of the range, end represents the end iterator of the range, and start value is the starting value from which consecutive values will be assigned. In our case, it is 0. So, iota of p plus n and 0 indicates that starting from the pointer to the first element of the array p, up to the pointer to the element after the last element of the array p plus n, starting from the value 0, consecutive values will be assigned to each element in the array. Initializing the parent vector p using the iota function ensures that each element is its own parent at the start of the union find algorithm. This sets the basis for tracking and combining sets of elements based on the connections found, allowing the algorithm to work efficiently and correctly. In conclusion, we use the union find algorithm to determine the number of provinces in a set of connected cities. The iota function initializes the parent vector so that each city starts as its own parent. By traversing the connectivity matrix and applying union and find operations, we efficiently determine the number of distinct groups of cities, each representing a province. This approach leverages path compression and union by rank to achieve near linear time complexity, making it suitable for large-scale problems. Testing the code thoroughly is crucial to ensure its correctness and performance. We encourage you to test your implementations and verify your understanding and improve your problem-solving skills.